So I guess everybody knew before they were here today that this is a very long story. And we're now to the beginning of the next part of the long story. I'm going to try hard to stay on time. There's 21 years more to go after the story that you just heard, which took a long time. So I'm going to pick up the story in 1994. And in 1994 was when we received, for the first time, project funding to actually build something, which is the LIGO detector, with all the responsibility of getting tens of millions of dollars a year for 20 years and defending it during a period where we saw nothing during that whole time. So the first thing that people should realize is that the National Science Foundation not only took the risks that Ray mentioned in taking on this project, doing the R&D and so forth, but after it was taken on, they had to defend a project with all the risks that it had for 20 years with essentially no results. We basically set various limits because we didn't see anything, but for no results. And so we're probably indebted more to the NSF than one can imagine in taking on such a project. We organized it by a collaboration between Caltech and MIT, and that shouldn't be lost in the story because we now have 1,000 scientists around the world, but we have at the center of all this what we call the LIGO laboratory, and the LIGO laboratory is the group that actually has built and made the detector work. The responsibility for the detector is Caltech and MIT's, and we've organized that as a project. We have about 150 technicians, scientists, and so forth. The scientists in this group do their science in what we call the LIGO Science Collaboration, but the instrument has been built by us. The present director is Dave Reitze, whose picture is up there. And the deputy director is Albert Lazzarini, and they're running it today while we're doing all this fantastic science. And earlier, after I was director, was Jay Marks, who led it during the crucial period when we took on advanced LIGO. Next, in about 1997, we realized that the Caltech and MIT collaboration didn't bring all the elements we were going to need to succeed at this project, and certainly not all the scientific ones. So we created what people have heard about today, and that is the LIGO Scientific Collaboration, bringing in talents varying from experts in lasers to experts on, and now, artificial intelligence, in order to take the whole breadth of talents that can be brought to this incredibly difficult problem and pull it together. That's grown from what started as tens of people in a collaboration run by Ray, who I appointed at the time to run the collaboration, to a collaboration now that's very democratic with elected officers and is run presently by David Shoemaker, by Gabriela Gonzalez during the period where we made the first detection. Before that, by Dave Reitze, who now is running the laboratory, and Peter Salson, who you heard about, was after Ray. This is a magnificent success of international collaboration, of the ability to bring in the talents that we need, whether it's technical, whether it's data analysis, whether it's theoretical, together, working together side by side. We have 18 countries involved in LIGO, more than 100 institutions, and about 1,200 collaborators, of which 1,000 were with us long enough that they were credited with authorship on our discovery paper. The interferometers themselves are organized with some critical people that have run it. From the beginning, we've had somebody who's at these sites that are distant and not close to a city and run by two people, originally Fred Robb and Mark Coles, who later went to the National Science Foundation, and presently by Mike Landry, who newly took over the Hanford Observatory, and Joe Giammi in Livingston. So if you visit either of those laboratories, that's who you see. And they're remote, one in distant Louisiana, far from any city, and the other on a DOE reservation in eastern Washington. Just to show you what things look like in the real hardware. This is a picture of LIGO if you walked into the big hall, where this is the vertex that Ray showed, where the light then goes out in two directions. This big thing here are called gate valves. They allow us to preserve the fantastic vacuum that Ray talked about that we need to while we work and evolve the instrument. These instruments that you look at here aren't quite as simple as what Ray showed, and part of that is building in enough flexibility, all these ports and all the ways of getting in, so that from the beginning we understood that if we're ever going to detect gravitational waves, what we built at the beginning wasn't going to probably make it. So we had to be able to evolve the instrument, and in ways that we weren't sure how to do it. So we, as much as possible, we asked the NSF for more funding at the beginning and made as flexible an instrument as we possibly could. We built it. By the end of maybe 1999, we had it built, and then we started making it work. And this picture kind of illustrates how we approach the next 15 years. We basically, this is the same curve that was shown by Ray, where it's limited on the left side by the shaking of the Earth, on this side by the amount of light, and in between by the noise on these test masses that we talk about. And better sensitivity is the bottom of the plot. It's the same scale that Ray showed. And this is the frequency band that's available to us to look for gravitational waves. It's the audio band where the Earth is the quietest. Each curve here is basically subsequently a different time. So our strategy basically was to turn this on. It was at whatever sensitivity it was. This isn't very sensitive. Lick our wounds, look at what we did wrong, what was limiting it, take time off, run it again, and it evolved to a better curve, a better curve, a better curve. This is about the first 5 years of the detector. We kept doing this for 10 years. At each time, we would search for gravitational waves. Each time, we wouldn't find gravitational waves. Each time, we would have a better limit, because this was better, on how well we knew they didn't appear. And so we wrote a series of papers, but they basically were null papers during that period. Along the way, we got to the point where we were as good as we had proposed, except maybe a little bit at the low frequencies. And that's this curve here. So this is the initial detector that we were funded for by the National Science Foundation on the same kind of graph, as good as we could. We knew very early, as Ray had indicated, that we wanted to do this in 2 stages, that we could incrementally improve things, but only so far without making some major changes. So we had done the detailed R&D necessary to develop the techniques and the apparatus itself, the detailed designs that would go into a second generation detector. And that was what we called advanced LIGO. Interestingly, we called it LIGO 2, but the NSF, in their wisdom, decided that we were sneakily talking about LIGO 1, 2, 3, 4. So they asked us to change the name, and it became advanced LIGO. With advanced LIGO, we then built it between 2010 and 2013 or so, and started turning it on. We basically had learned a lot, so we turned it on a lot faster than we had the initial LIGO, getting near design sensitivity. By 2015, it started to work well enough so that it was better than what we had built for initial LIGO, and that is shown here. The key people, by the way, for advanced LIGO, some of the key people I show over here. Dennis Coyne, who was shown earlier, has stayed with us as our chief engineer and was the engineer responsible for the fantastic engineering that goes into advanced LIGO. David Shoemaker, who's running the collaboration now, was basically the main scientist responsible for advanced LIGO. And Peter Fritschel for the incredible optics that we use and the way the interferometer works itself, and 2 people, one in each laboratory, who have been the most responsible for making this thing actually work in the field. And so we started to make it work, and the two detectors are in the two different colors here, and what they indicate is that despite the fact that they're physically in very different locations, they basically, in design, and as long as we do the same thing at the same time, they work essentially identically to each other. At this point, this had improved about a factor of 3 beyond where we were in initial LIGO. Our goal was to improve things a factor of 10. This is improving the sensitivity a factor of 3. And what to realize is that the sensitivity tells you how far out you look in the universe. So if we increase the sensitivity a factor of 3, we actually improve how much of the universe we're looking at by the cube of that, because that's the volume that's scanned. So an improvement of a factor of 3 basically gave us the ability to do what we had done in initial LIGO or more in 1 year, what we could have done in 27 years with initial LIGO. So we decided not to go all the way to here, but have a similar strategy to what we had in initial LIGO and use this as the first search. Because we had improved the concept for how we treat low frequencies, which was described by Ray, the improvement at, say, 40 hertz was actually a factor of 100, shown here. A factor of 100 is cubed in terms of the sensitivity we get, so we were really 1,000,000 times better than we were in initial LIGO. And that answers a question that's often asked to us: how could we turn this thing on, and after a few days, which is what happened, make a discovery when we had run it for 10 years before that, or almost 10 years. And it's really this factor of 1,000,000. So we turned on advanced LIGO and made that improvement. Again, this is just a picture to emphasize that the big improvement that made this detection, maybe the take-home message, if you want to tell anybody why and how we made the detection, was the improvement in this nice quadruple and fancy suspension system developed at Glasgow, and the isolation from the Earth by seismic isolation from the Earth by a set of essentially shock absorbers and these active seismic feedback systems that Ray mentioned, that, by the way, the reason they're so hard, it has to be done directionally, differently than the earphones in the airplane. We have to know where the Earth is shaking us, what direction, and correct for it. And that makes the system quite a bit more difficult. We turned on, and a few days later, this is what we found. So this was September 14th, 2015. 21 years after we received project funding in 1994. Not what my fantasies were, most of us, for what we'd first see. I would have expected, if I thought about what we would see, that we'd start to see hints of gravitational waves where our detector wasn't quite sensitive enough yet to make it definitively, and that we keep working in the future at making it more sensitive. We were lucky instead. We, of course, made big improvements, but we immediately saw a signal that stood out and looked very much like you'd draw to show somebody what we were doing. This is two different traces. One of them at the laboratory in Eastern Washington, Hanford Laboratory, and one in Louisiana, and they should look essentially alike. You'll notice the left-hand side is strain, the word that Ray used, and the scale is the scale he also showed, 10 to the minus 21. So the scale that we were detecting and got to the sensitivity to detect, and also the scale that had more or less been predicted by the range of sources that we talk about, was 10 to the minus 21, and that turned out to be, after all these years, right. And these are the two traces. If I take the two traces and plot them on top of each other and slide one slightly from the other one by 6.9 milliseconds, then they sat essentially right on top of each other, as you can see here. And the difference between the time between the two, I'll point out in a minute, gives us information that's crucial, especially for the future. So those are the two detections. By the way, we made a decision in 1994. Finally, we had to make the decision in 1994 how to orient these two detectors relative to each other. They can't be exactly the same because the Earth curves by 16 degrees between Livingston, Louisiana, and Hanford, Washington. But there was a rather large debate whether we take the two L-shaped detectors and make them parallel to each other or rotate them by 45 degrees. The reason you would rotate them by 45 degrees is it gives you the ability to extract more physics. That is, there's a polarization in these gravitational waves, just like for electromagnetic waves. So the argument to rotate them is exactly that. The argument to put them in parallel is what I showed you here, that we could put one on top of the other. We did it one on top of the other in conservatism, and of course, it's what made one event so convincing that we could put one on top of the other. But we couldn't tell the polarization information. That has come, and I'll talk in a minute, by adding a third detector that is oriented separately from us. That's the Virgo detector, and that has started to give us information on the polarization. We detected this event in September of 2015. Did we immediately know it was gravitational waves? Not really. Most of us, or some of us at least, had deep worries how we might be mistaken, how we might be fooling ourselves, or how we might be being fooled. Those two questions, basically in translation, were that we turned on a new apparatus, and in turning on a new apparatus, maybe it could generate some sort of shaky signals, but they weren't real. And in order to test that, you have to run it for some period of time. We calculated how long that had to be, and it was basically a month. In a month's time, we could look at all the bins of time in the two, correlate them together, and see what the probability is that you could get any sort of signal like this in the detector. And that's calculated to be a magic number in physics when you believe something, which we call 5 sigma, or the probability is less than 1 in some hundreds of thousands of years. So basically, that was the first thing. The second problem was maybe somehow we were being fooled by some mischievous people or person who has superposed this on the data. And we just looked at the data, and it really wasn't there. That, again, had to be studied in great detail by following. The idea was the following. The data comes together at Caltech, and from that time on, goes around the world. In fact, this first event was seen first in Germany. It was the middle of the night in the States. And the data comes together. Once it's together, you could imagine somebody superposing an event on top of the data. To resolve that, we have to take it back to the laboratories where we can trace the signals and what they recorded along the way. And that required another study, which took about a month. So by middle of October, I think we had really confidence that we had made this discovery. We spent maybe another month seeing how well it fit general relativity. Spent another month writing it up in great detail. Writing it up in a way that we thought could be read by the world and not just by experts in the field, arguing about whether it should be called an observation or a discovery and things like that, with 1,000 people weighing in. And you can imagine somehow making that converge was a problem. We finally were ready to submit this to Physical Review Letters, our choice of where to publish this, by early December of 2015. We were about a week late because we were arguing too long on which adjectives to use in the paper. And at that point, Physical Review Letters, who had agreed that they would allow us to make the article longer than the standard article, and that they would review it specially, both very secretly and quickly, informed us that we were now too close to Christmas and they couldn't do it. So we held the article until January, and interestingly, our second event, which I show now, came on December 26th. So when we announced this event in February of 2016, we knew, but we didn't yet bring that to the public, that we also had a second event. So as convincing as the first event was, we all had a second event. It looked very different. You can see this has many, many oscillations. It's smaller, but we detect it as well because there's so many oscillations. That's a reflection of the fact that they're lighter, the two black holes that are colliding. It's also black hole collisions. This graph here just illustrates, it's the so-called chirp graph. This is basically time going this way, frequency going this way. It gets louder as the frequency goes up, and it's the so-called chirp that we describe as a signal. The second one, which is weaker, but in there longer, so we are able to pull out the signal, is down here. But if we look at basically the low frequencies that weren't available to us until we made the big improvement in the suspension and the isolation system, both of these signals were enabled by making those improvements at low frequencies. Of course, we've kept running. We finished that first data run with these two events in January of 2016. And at that point, we changed things, fixed things in the same spirit that I presented our activities through the period of initial LIGO. And we started a second data run, which maybe for most of us, we expected couldn't possibly be as exciting as what we saw in the first data run. That turned out to be wrong, as I'll show you. In the second data run, I show here we haven't analyzed all the data yet. We haven't made all our reports yet, but this is where we are today. We basically have reported 5 observations of probably black holes. One of them we don't call a black hole just because it's further away and doesn't give us quite the 5 sigma significance as a single event, but otherwise it appears to be like the others. So we have a set of events which start to let us look at distributions of the alignments of spins, the masses of them, and the difference in how long they are is the difference in how much their masses are, and so forth. So the 5th one here actually has a different significance. That's this one here. The dates are the 17th, the 8th month, the 14th day in 2017. So just this last August. So this last August, we detected an event that at the same time was detected for the first time also in the Virgo detector in Italy. The Virgo detector is very much like LIGO. I don't have time to show some interesting differences in how they approach the problem, but it basically has similar sensitivity once it's fully operational, will have similar sensitivity. This was begun by 2 scientists in parallel with the efforts that were described by Ray, Alain Breillet and Alberto Giazzotto. And in the present day, run a little bit like us, having a laboratory where the director is Federico Fermi, and the spokesman, who I think is here today, is Jo van der Brand from Holland. And it's very near Pisa in Italy. It's not just the confidence, which of course matters, that somebody independent sees the same thing. That's great. And at this point, we don't really need that. We're pretty convinced that we're seeing gravitational waves. And we were in competition for 20 years, I think, to see who could see gravitational waves first. But it gives us new information, and that's shown here. With just the first detectors, we were able to locate, even on the first event, that it came from the southern hemisphere, and we knew to some number, 600 or 700 square degrees, where it came from. And the various events are shown here in how well we could tell where they came from before we turned on the Virgo detector. The Virgo detector, once it's on, because it gives us triangulation in where the signal they see compared to ours, where we take the time difference in the arrival time at the different detectors and the difference in the signal, because the antenna patterns are somewhat different, gave us this signal down here. And you can see that we now can locate, with the addition of Virgo, the location on the sky where a gravitational event came very accurately. This is something we've always wanted to do. And luckily for us, this happened just in time. And I'll show you that in a minute. First, let me reflect on what we found so far, seeing 5 events. We've seen where this is mass, and this is just the time passing, the number of events. These are each symbolically 2 black holes coming together, making a heavier black hole. They're all up here on the plot where this is mass. What was expected was black holes that would be down here. So we immediately, something we've always thought, using gravitational waves, would see different phenomena that are seen in electromagnetic radiation. And what we saw was large black holes. They're not expected. Just qualitatively, the reason is the progenitor, or the heavier object that makes these black holes, is supposed to be a heavy star that decays and makes a that dies and collapses and makes a black hole. There aren't, we believe, very heavy enough stars to make these very easily. There has to be either a special place in the universe where it's low enough metallicity or doesn't have heavy elements around so it can live longer, or dense clusters or primordial production that made these black holes. And that's our next problem, like all these problems in physics, is where do these black holes come from? There are handles on it. We hope to get more information on the spins, on the orientations, on the distributions, and to be able to resolve that. The second thing that has come out of the very first events is tests of general relativity. This is a graph where we just put in a form that would be qualitatively different from general relativity, just to test it, not a particular theory. One limit of that is to look at the physical place where you would have connected to the transmission of gravitational waves what we call a graviton. Very much like for electromagnetic waves, we have a photon. Or for particle physics, there's all the particles. A graviton, if it existed, it does not exist in Einstein's theory, could have a mass. And what we're able to do is, if it had a mass, it changes the detailed shape of the trace that we looked at. And we're able to say already, just based on these very first observations, that if there is such a mass, it's less than 10 to the minus 23 electron volts over c squared. So those are tests. The next was a rather fortunate coincidence. We got Virgo into our system, working together 2 weeks before this happened. Later in August, by the way, we were scheduled to turn off at the end of August, so this happened, fortunately, just before we turned off. Well, for the first time, we saw a second kind of event. The merger of a binary neutron star system instead of a binary neutron star system instead of a black hole system. What is a neutron star? Again, Ray mentioned neutron stars. It comes from the collapse of a star also, we believe. But it's dense nuclear matter instead of a black hole. If it's dense nuclear matter, if we have 2 objects going around each other, it has all kinds of nuclear effects in addition to just the general relativistic merger. And this is nuclear physics in extreme conditions. And we can then see all kinds of effects, including the fact that the nuclear effects can give and emit light in various ways. We basically could tell from what we saw that these were much lighter, like neutron stars are supposed to be, than the black hole events. They were a distance much closer than that 50 megaparsecs instead of 20 times that we saw for the black holes. And fortunately for us, the signal was also seen 2 seconds later in an astronomical instrument. That was the Fermi satellite that monitors gamma ray bursts. This is a picture of our signal and put on their trace, and where they saw a signal. Over here is the same pictures of the location on the sky. Our location on the sky is these long pictures here if it was just LIGO. But when we add Virgo, it's this little ellipse here. And this is the position as determined by the Fermi satellite. One thing that makes me feel great is that we're the ones that actually have the better location, even though we're beginners at this game. So, and that's very important for the future. So this picture is what we think is the indication of what the future is going to portend. This particular event, then having the confidence that it was seen both in an electromagnetic instrument, the Fermi telescope, and us, could be studied for hours, days, and weeks after that, and has been. Looking at gravitational waves, of course, looking for it with neutrinos, looking with visible and infrared light, radio waves, gamma rays, and X-rays, and so forth. Using this, a whole set of collaborations and conclusions have been made from this one observation already, which, by the way, we announced only a little over a month ago. 2 weeks after the Nobel announcement, we announced the merger of two neutron stars. So even after whatever we got this prize for, we're still producing very interesting new things. I'll just give you a glimpse, I'm out of time, at a few of the different kinds of phenomenon that are and interpretation that came out of this single first coincidence event with electromagnetic instruments, kind of to wet your tongue at what's going to happen in the future. The first is an independent, pretty independent measurement of what's called the Hubble constant. This is basically the rate at which the universe is expanding. It's done by in this case, optically identifying what galaxy it was in, and then otherwise from the information we have in the gravitational wave signal. And the answer, this so-called Hubble constant, is independent of and consistent with the answers that came in electromagnetic interactions. The second, which I won't go through in any detail, is that there's been a lot of phenomenology of what happens when objects like these neutron stars come together. We all know what a supernova is, the collapse of a star when it gets old and dies. This is tabbed a kilonova, the consequence of this coming together, and that's been studied now in all these different instruments and put together and compared with some of the phenomenology that's been developed for a kilonova, and at least the general idea confirmed. One consequence which is interesting is the possibility that we have actually figured out or seen what makes heavy elements in the sky, in heavy elements. A puzzle has always been, how on earth do we have very heavy elements? Where did they come from? You can go on a mine and find gold or platinum or other heavy elements. Where do they come from? We know most of the universe is made out of hydrogen and helium. We know how to make everything up to iron very easily. It's made in the same fusion process that makes the sun. The sun burns. But making heavier elements in nature, we don't really know. We do know how to make them in the lab. We make them all the time, and the periodic table has gone up quite high. We basically take a heavy element and bombard it with neutrons. Sounds familiar, neutron stars. So the neutrons are the way we do it in the laboratory. So the idea is very tempting that maybe in nature it's collisions like we just observed, that is neutron star collisions, that made heavy elements. This graph here is one phenomenological interpretation of that. And the yellow parts, which you'll notice are mostly yellow for gold and platinum, which you might have on your hand, come from merger of neutron stars, at least in this analysis. And so maybe all the gold and platinum that we sell on the Earth, we finally discovered comes from collisions like we've just announced, a rather interesting conclusion. Lastly, I just want to end with the future for a minute or two. We have now 3 detectors working. We'll soon have 2 more. We have one we're building in India, a LIGO, with the collaboration of the Indian physicists and Indian government. That'll be ready in the 2025 era. There's one in Japan that has some advanced techniques, which I'll mention, which should be working within the next few years, giving us better localization. This is an incremental plot of how well we think we'll be able to locate the position on the sky as we move into the 2020s. And you can see that with the addition of the other detectors, independent of where something comes from, we should be able to tell very well where it is and combine then with electromagnetic information. We have ideas and also plans for the future, and I want to end on that. First, as I showed you, we're still about a factor of 2 away from the design of advanced LIGO. That we will do over the next few years, again, in a matter of steps. And that gives us almost a factor of 10, 2 cubed in the rate or the significance of individual events. We have concepts for getting beyond that. We know that we should at least think and do the R&D and possibly ask to be funded for a concept that would exploit our sites where we have LIGO to their fullest extent. And so we've basically done conceptual designs of that. We can improve by making a much heavier test mass, by using a different material in the mirrors. We're presently looking at silicon, by lowering the temperature modestly, by improving a limitation we have, that is the coatings, the optical coatings on the mirrors that Ray showed, and by making yet a more powerful laser. If we do that, we can get down to the black curve that's shown in this plot here. And that will enable us to have more cosmological reach, which will be talked about by Kip, some of the ideas of what we might be able to do. Improve signal to noise, what we've learned is that we need to have events where we have such good signal to noise that we can determine things like the orientation of the spins of the black holes and so forth. And an event rate that's maybe 10 times advanced LIGO if we put in all these. This will require R&D, and we haven't yet the funding and haven't formally proposed to do it. The next steps are to do other reactions that we can do on the Earth's surface, but also, and this is some of those as possible, and Kip will talk about those, but it's already basically in this community ideas that are fairly well developed for how you would move to the next generation detector. It's completely possible. We don't see any great technical hurdles in extrapolating this up to a detector that's a factor of 10 or so better than present detectors. What's the right detector is what we have to work on. And to do that, we have to set our priorities in science. We can't do everything. There's 2 main concepts right now on the table. One is to go underground, make the detector cryogenic so it's cooler. This very much helps the lower frequencies. Where going underground, there's less shaking of the Earth, cooling the detectors, you have less thermal noise. This is a concept that's been developed in Europe, and it's called the Einstein telescope, and they've been working on it for about 5 or so years, and it's pretty firmly designed. Maybe not costed, but at least the concept is fairly designed. In the US, we've been looking at another approach, which is to make basically a LIGO-like detector, but much bigger. That is to make a detector that's 40 kilometers instead of 4 kilometers. You'll remember from Ray's talk that length basically you gain linearly. So if we can make it 40 detectors and do everything else as well, we're 10 times better, basically. And this would be then on the Earth's surface, which is cheaper, but we have to worry about the fact that there's Earth's curvature in that length. It has arms that are 40 kilometers and basically would have to have the instrumentation that we use in initial LIGO. This R&D is just starting. It's being led by Matt Evans, who's probably somewhere up here. I can't see him. In developing a group that actually will develop this concept. Over the next few years, we hope to develop both the science priorities so that we know what has to be done, what we want to do, and to begin to do the serious R&D that would go into such detectors. Overall, and this is just a precursor of Kip's talk, the science as we move to the future is going to be very much like what has happened in astronomy. As astronomy started by Galileo looking through a telescope at visible light, we know now we do astronomy by looking at visible light, X-rays, infrared, so forth and so on. The same thing is true here, that we can look at gravitational waves in a particular frequency band on the Earth's surface. It's what's available to us where it's quietest, and that's the audio band. If we want to look at other frequencies, we have to use different methods. The most close to being done, because it's approved and funded, is to do an experiment in space. It's called LISA. It'll move into the frequency band of 10 to the minus 1 to 10 to the minus 4 hertz instead of 10 to 10,000 hertz like ourselves. And that covers a different frequency band. And what's shown above, and I'll leave that to Kip to talk about, is both some of the same phenomenon looked at at earlier time in their evolution and other phenomenon that never reach the frequencies that we get on the Earth. You can look at yet lower frequencies. One concept that's being developed now that I don't have time to talk about is to use timing from radio pulsars. And that's being looked at, looking for signals at very lower frequencies by monitoring the time coming, and we're looking for changes from a set of radio pulsars. And lastly, there are ways to get the effect of gravitational waves from the early universe, which is the most interesting of all in most of our minds, when and if it can be done. And I'll leave it to Ray to talk about those. Thank you.